Hello everyone, my name is Simran Narang and I am working as an assistant professor in School of Engineering and Technology, CTU University, Ludhiana, Punjab. My today's topic is semiconductor devices. Semiconductor materials. Semiconductor materials are the materials which have electrical properties somewhere in the middle between those of a conductor and an insulator. They are not good conductors nor good insulators, hence their name semiconductors. Silicon and germanium are the examples of semiconductor materials. Next are the characteristics of semiconductor materials which make semiconductor materials good or better over the conductors and insulators. First property is conductivity. Semiconductors have intermediate conductivity compared to conductors and insulators. They exhibit conductivity between that of good conductors and insulators. In pure form, semiconductors have limited conductivity due to a small number of charge carriers. However, their conductivity can be significantly increased by introducing impurities through a process called doping. Next property is band gap. One of the defining properties of semiconductor is their band gap. Unlike semiconductors which have overlapping valence and conduction band and insulators which have a large band gap, semiconductors have a moderate band gap. This band gap determines the conductivity and electrical behavior of semiconductor devices. Third property which makes it different from conductors and insulators are variable conductivity. The conductivity of semiconductors can be modified by applying external factors like electric field or by controlling temperature. This controllable conductivity allows for switching behavior, amplification and signal processing, forming the basis of electronic devices like transistors and integrated circuits. Next are the importance of semiconductor materials in different areas of life. First importance is in the field of scientific research and innovation. Second is in optoelectronics. Third, economic impact and industry. Fourth one is electronics and integrated circuits. And fifth one is communication and information technology. Semiconductors are basically divided into two parts, intrinsic semiconductor and extrinsic semiconductors. Intrinsic semiconductors are also called as pure semiconductors. Extrinsic semiconductors are called impure semiconductor. Extrinsic or impure semiconductors are further divided into two types, p-type semiconductor and n-type semiconductor. First, we will discuss about the intrinsic semiconductor. A semiconductor material in its pure form is known as an intrinsic semiconductor. Thus, the intrinsic semiconductors are chemically pure, that is, they are free from any kind of impurities. The number of free electrons is equal to the number of free holes in the intrinsic semiconductor. The common examples of intrinsic semiconductors are silicon and germanium, which are naturally obtained from the nature. In a pure intrinsic silicon or germanium semiconductor, each nucleus uses its 4 valence electrons to form 4 covalent bonds with its neighbors. Since there are no excess electrons or holes, as we can see in the diagram, so in this case, the number of electrons and holes present at any given time will always be equal. Next is doping. In semiconductor production, doping is the intentional introduction of impurities into an intrinsic semiconductor for the purpose of modulating its electrical, optical, and structural properties. The doped material is referred to as an extrinsic semiconductor. The doping of semiconductor increases their inductivity. Extrinsic semiconductor. This is the second type of semiconductor devices. When a small amount of chemical impurity is added to an intrinsic semiconductor, then the resulting semiconductor is known as extrinsic semiconductor. The extrinsic semiconductor is also known as doped semiconductor. Extrinsic semiconductors, as we have already discussed, is divided into two types. First one is p-type semiconductor and n-type semiconductor. P-type semiconductor is obtained by the doping of pentavalent impurities, and n-type semiconductor is obtained by the doping of trivalent impurities. Let us discuss it one by one. P-type semiconductor. The p-type semiconductor is formed when a trivalent impurity such as gallium and indium is added to a pure semiconductor in a small amount, and as a result a large number of holes are created in it. In this semiconductor, the majority of charge carriers are holes, whereas minority charge carriers are electrons. The density of holes is higher than that of electrons, and the acceptor level mainly lies close to the valence band. As we can see in the diagram, a positive charge hole is created when 3 valence electrons of the impurity bond with 3 of the 4 valence electrons of the semiconductor and having 1 electron short. The covalent bond cannot be completed, hence the missing electron is known as hole. Next one is n-type semiconductor. The n-type semiconductor is formed when a small amount of pentavalent impurity such as arsenic or phosphorus is added to a pure germanium or silicon crystal. In this semiconductor, the majority charge carriers are electrons, where minority charge carriers are holes. The density of electrons is higher than that of holes in n-type semiconductors. As we can see in this diagram, in this case the impurity adds 5 valence electrons to the lattice while it can only hold 4. This means that there is now one excess electron in the lattice, and this excess free electron adds up to the n-type semiconductor. Each pentavalent impurity atom is said to donate 1 electron to the n-type semiconductor. Hence, it is called donor impurity. Thus, there are more electrons than holes in the n-type semiconductor. P and n-type are of no use when they are separately, and if we combine them, P and N junction diode is formed, which is of very much useful in the everyday life. So, next topic is about the PN junction diode. A PN junction diode is an interface or a boundary between the two semiconductors materials, namely p-type and n-type. Means it is formed by the combination of p-type and n-type. Below is the symbol of PN junction diode. In this symbol, the triangular represents the p-type and the vertical line represents the n-type. As we can see in this diagram, in the right hand side there is a p-type semiconductor, and in the left hand side there is a n-type semiconductor. In the p-type semiconductor, the majority are holes and there are lesser number of electrons, and in the n side there are majority of electrons and lesser number of holes. And between the p-type and n-type semiconductor there is a depletion region. This depletion region is formed when the electrons from the n side diffuse into the p side, then the depletion region is created in between that. Depletion region is also called the depletion layer. Depletion layer. When the PN junction is formed, a few electrons from the n-type diffuse through the junction and combine with the holes in the p side to form negative ions and leave behind positive ions in the n side. This results in the formation of depletion layer, which acts as the barrier and does not allow any further flow of current from the N region to the P region. Next is biasing, like what happens when we attach a battery to a particular PN junction. That attachment of battery or that connection of external voltage to the PN junction diode is basically called the biasing of PN junction. A PN junction connected to an external voltage source is called biased PN junction diode. By applying any external voltage source across a diode, we are able to control the width of depletion layer. So by applying any kind of battery or any kind of voltage to a particular PN junction diode, we can control its width, and hence we can control the flow of current which is flowing across the PN junction diode. There are two types of biasing. So first biasing is forward biasing and next one is reverse biasing. Let us discuss it one by one. First one is forward biasing. When a diode is connected in a forward bias condition, a negative voltage is applied to the N-type material and a positive voltage is applied to the P-type material. If this external voltage becomes greater than the value of potential barrier, which is approx 0.7 volts for silicon and 0.3 volts for germanium, the potential barrier opposition will overcome and current will start to flow. This is because the negative voltage pushes or repels electrons towards the junction, giving them the energy to cross over and combine with the holes being pushed in the opposite direction towards the junction by the positive voltage. This results in characteristic curve of zero current flowing up to this voltage point called the knee point on the static curve, and then a high current flow through the diode with little increase in the external voltage. The application of forward biasing voltage on the junction diode results in the depletion layer becoming very narrow or thin, which represents a low impedance path through the junction, thereby allowing high current to flow. This is the circuit diagram of forward biasing voltage. Here the N region is connected to the negative side and here the P region is connected to the positive side, which results in the narrowing of depletion layer. This is the VI curve or forward characteristic curve for the forward current and forward voltage. At 0.7 voltage, there is a knee voltage. After this, there is high rise of current occurs. Next one is reverse biased. When a diode is connected in a reverse bias condition, a positive voltage is applied to the N-type material and a negative voltage is applied to the P-type material. The positive voltage applied to N-type material attracts electron towards the positive electrode and away from the junction, while the holes in the P-type end are also gets attracted away from the junction towards the negative electrode. The net result is that the depletion layer grows wider due to lack of electrons and holes and presents as a high impedance path. Almost an insulator and a high potential barrier is created across the junction, thus preventing current from flowing through a semiconductor material. As we can see in the diagram, N region is connected to the positive side and P region is connected to the negative side, so that the N region gets attracted to the positive side and P region gets attracted to the negative side. Thus, result is that the widenation of the depletion layer, it's get elongated in the opposite sides. If the reverse bias voltage VR applied to the diode is increased to a sufficiently high enough value, it will cause the diode's PN junction to overheat and fail due to avalanche effect around the junction. This may cause the diode to become shorted and will result in the flow of maximum circuit current, and this shown as a step downward slope in the reverse static characteristics curve below. This is the reverse characteristic curve for the reverse biased voltage. A reverse bias voltage and reverse current is shown in this direction, in this diagram. At Vz we are having reverse breakdown region. The Vi characteristics, the curve between voltage and current across the circuit defines the Vi characteristics of PN junction diode. The x-axis represents the voltage while the y-axis represents the current. This is the holistic diagram for a PN junction diode for the Vi characteristics. In the first orbit, it represents the forward current and forward voltage, and in the fourth quadrant, it represents the reverse voltage and reverse current. At a point, we are having knee voltage in the forward current and forward voltage, and at the reverse voltage and reverse current, we are having reverse breakdown voltage. Next are the applications of PN junction diode. First application is the rectification. One of the primary functions of PN junction diode is rectification. They allow current flow in only one direction while blocking it in the opposite direction. This property is crucial for converting alternating current to direct current in power supply and rectifier circuits. Rectification is a fundamental requirement in various electronic systems, including power electronics and signal processing. Its second application is signal detection and demodulation. PN junction diodes are widely used in radio and communication circuits for signal detection and demodulation. They can extract information from high frequency carrier waves and convert them into useful signals. This property is essential for receiving and processing radio signals, telecommunications, and data transmission. Next is switching. PN junction diodes can serve as electronic switches in circuit. When a diode is forward biased, it conducts current and acts as a closed switch. When reverse biased, it blocks current and acts as a open switch. This property is utilized in digital logic circuits, switching power supplies and electronic control system. This is all about the semiconductor devices. I hope you get valuable information from my lesson. The take-home message from my session is it is essential to embrace the benefit of electronics while also considering the responsible use and disposal of electric waste to minimize electronic impact. Thank you.